And this is where integration has a much longer history than derivatives. Areas were important to figure out, but life isn't always straight lines for figuring out what an area should be. So if I wanted to find this area under this cosine curve, the problem is the curve is bent. But if I wanted to get an estimate of it, I could, and this got, oh, I can't read, the computer moved it, but it's supposed to be matched up better. I could get a good estimate if I used some small rectangles. Does yours match up? Oh, yours is pretty nice. But you notice that your rectangles are just a little bit, that answer would be a little bit too small, because I made all the rectangles a little bit below the curve. But actually it looks pretty, like if you added up all those rectangles, it would be pretty close. I'd be pretty happy with that. And then mathematicians said, well, if you're happy with those rectangles, imagine cutting them in half and making them smaller. Couldn't you get more accurate? And the answer was yes. And this led to what Archimedes called his method of exhaustion. He called it the method of exhaustion, he says, because you could be like, if you're willing to keep going, cut them in half again, make them smaller, you get closer. But if you're not happy with that, you could do it again, make them even smaller. And you could do 100 rectangles and add them all up, which would be tiring, hence the words method of exhaustion, but you'd get closer. And in fact, if you kept on going, Archimedes was on the idea of a limit that eventually you would get so close that you would basically get the answer. And the crazy thing is, okay, we'll start off with a really easy visual. I watched the following. I'm going to just do y equals 2x plus 2. Yeah, that's nice and easy. That would be this line, right? And if I went over 1, 2, 3, 4, would you agree that you would have the point 4, 10? Wow, that's a nice straight line. And if you wanted to figure out this area, you could take this shape that we're left with and break it up into a rectangle. This area would be 2 times 4, which would be 8. And this side is 4, and if this is 2, this is 8. Base times height, 32 divided by 2, this would be 16. The whole area would be 24. Okay? Watch the following. If I took the integral of 2x plus 2 dx, this is an easy integral for us to figure out. We're going to get introduced to the definite integral. The definite integral, this time we are going from 0 to 4. We're not doing the whole thing. We're just going from 0 to 4. With the definite integral, you can integrate. I hope you can see this is x squared plus 2x. And with the definite integral, we're not going to put the plus c. We're going to do a 4 and a 0. And we're going to plug in 4, and we're going to plug in 0, and subtract. So plugging in 4 minus, well, plugging in 0, that one I can do really quickly, mental math. But plugging in 4, you will get 16 plus 8, 32, which 16 plus 8 matches up with the area under that curve. Which is kind of cool, but we could have done that with a straight line. But now, how hard would it be if I gave you, just to make our, let's just take a graph. And let's go up to 2. We got the point 2, 4. That area would not be something we could easily do. However, the integral from 0 to 2 of x squared dx would equal x cubed over 3 from 0 to 4. I actually think my notation is off a little bit. Double check the IB notation here. I should put it in big star brackets there. And then plugging in 4 is not hard. 64 over 3, plugging in 0. This area is actually 21.3 repeated. 64 thirds. And it works. We won't go into the proof of how it works, but the idea is that the integral is basically getting smaller and smaller rectangles, the limit as they go to 0 in width, and adding them all up will give us our area. And the reason there's the subtracting thing is because if I just wanted to find between 2 and 3, the 3 would go all the way back to 0. Then I would subtract 2, which would go all the way back to 0, leaving me with just the area in between 3 and 2. And this is the definite integral. And it actually finds an area underneath a curve, which is terribly simple as far as like, we just found that area under that parabola, 64 over 3, which is a terribly crazy thing to figure out. You would have no way of doing that other than estimating up to now. And it's a technique that is extremely simple if you know how to integrate. So, the number on the bottom is the lower limit. The number on the top is the upper limit. What do? We find our integral like we normally would. We put it in square brackets and go from A to B. And because you're plugging, the reason you don't need the plus C is because you're plugging in one and subtracting the other one. If there was a plus C and you subtracted the other plus C, they would just go away. So we can just ignore them for that reason. So, what we have to do is we have to integrate. Then we take one and plug it in and subtract the other one. And you can mess around. Like normally you would think B should be bigger than A, but it doesn't necessarily have to. Your calculator has this built in too. So we can go to our calculator. Let's just put in x squared. So there's our regular parabola. What we can do is we can graph it, go second calculate, number 7 your integral from 0 to 2. Is that what we found, or did we find? Yeah, no, 0 to 4. We found 0 to 4. 21.3 repeated. And it actually colors it in and everything for you. Nice. We can find all sorts of crazy areas. We could go back and go sin x. Graph my sin x graph. Maybe I want to check it from 0 to pi. How much is that area under there? 7 from 0, pi. Color that in perfectly. And the area is pi. Fascinating. Isn't that cool? That the area under a sine curve from 0 to pi is actually has an area of pi. Okay. right? How important is this? It is important. Sometimes I teach you things on the calculator, I'm like, that was neat, you're not going to use it. This, if you get a calculator part of an exam that asks for a definite integral, you want to be able to find it quickly rather than have to do too much mathematics. So if you have access to your calculator, this could be very nice. Okay, we also have under the math button. So I hit the math button, I go to number 9, right? Finint, right, there it is, finint. Push enter. If you have a newer calculator, it looks like this. If you have an older calculator, have fun. The newer calculator, so we could go from 0 to 4 of x squared dx. And we got 21.3 that way too. So you can type it in just like you would expect. If you have your TI-83, you're going to have to figure out what to type in where. I think math 9, you would type in x squared, comma, 0, comma, 4, x. Oh, there it is. Function, then x, then, oh, so I needed x, then 0. One of the things we are going to do, since this is a lot nicer than having that, one of the things that we're going to make sure before the exam is we're going to get the IB calculators and make sure they have the newest operating system up to date so that when you type this in, that would show up. Okay? But if this isn't working, you could use the other method, right, where you graph it first and then do second trace and do the integral from the graph. That one's probably even easier to use. Okay, so from 2 to 3 of 3 over x of dx. So we could do this with our calculator either by, so Eddie on yours, I would say graph it and use your graph. For the rest of us, you could choose whether you want to graph it or whether you want to use the math button, number 9, and type it in. 2.748. Very nice. That's weird. Okay. Part B. Wow, why are there no X's? Does yours have an X here? Is it missing it too? Yours is good? Oh, one more. So pretty cool that we can do this all in our calculator. Again, if you have a calculator, this is faster than actually trying to figure out, right? This one you could do, this is e to the 3x divided by 3. This is going to be minus 2 natural log of x plus 1. It is possible to do these. And then plug in 1, plug in 0, and subtract them. However, if it's calculator part, it is a lot easier just to type this in. Oh, and we have a bunch. You know what? We will leave the rest for you to do on your own. Maybe we'll have time at the end. But they're not hard if you can use a calculator. Some properties. Some of them should make sense. If you are trying to find the area under any curve, and you went from the same value to the same value, that would just be like a thin straight line. It would have no area whatsoever. So that's 0. If you went from A to B, it'll be exactly the negative as if you went from B to A. So here is just a picture to figure that out. So let's say you had a parabola like this, and this was A, and this was B. Great time to use a crayon. This part colored from A to 0 would be the integral from A to 0. This part colored in blue would be from B to 0. If this area, if the blue area let's just imagine we figured out that the blue area was 10 and the green area was 4. From A to B then, can you see would be 6? Because you would have all of 10 minus 4. If you did it the opposite way, then you would have gotten 4 first, and then have to subtract 10 would give you negative 6. So if our bounds are flipped, we'll get the same answer, but one would be positive and one would be negative. Because either you're going to do 10 minus 4, or you're going to do 4 minus 10, depending on the order of the numbers. Because what's happening is when you plug in the value, that value gives you the area all the way down to 0. And then the other one would give you the area down to 0, and subtracting would make that difference. Now it should make sense that if we added a C value in between, that the area from A to B would be the same as the area from A to C plus the area from C to B. So if you add a C value in between, and then technically it doesn't even have to be in between, this will work no matter where you put that C value. But it's easy to visualize if I put it in between. That the area from A to C plus the area from C to B should be the complete area from A to B total. And here we have the same rule that we did with indefinite integrals. if you have some constant in there, you could pull that out in front and still do the indefinite integral. So for example, do you remember that we went from 0 to 4 on x squared dx, and we got this answer to be 64 over 3? If you wanted to do 3x squared dx, you could very quickly say, well, I've already figured out, I can pull that 3 out in front, I've already figured this out to be 64 over 3, so this will just be 3 times 64 over 3, and its area will be 64. So that property can become very helpful with definite integrals, because if you know part of it already, like if they tell me this, I can do this by just pulling the 3 out in front. This part I know is 64 over 3, and I can just multiply it by 3, rather than calculating it all again. And just like in other integrals, if you're adding or subtracting, you could do each integral separately. And the IB exam likes to play around with these rules. And questions will look something like this. We have some function, we don't know what it is, f of x, but we know the area between 0 and 2 under the curve is 4. From 2 to 5, the area is 12. In g of x, the area from 0 to 2 is negative 3, and from 0 to 4 on g of x is 6. If you took f of x multiplied by 3 and subtracted g of x, what would the area be under the curve from 0 to 2? Whew. Okay, so we're going to use our rules and try to rewrite this so we can steal answers from what was given to us. First of all, we have a rule that says if you're subtracting, you could do those separately. So I could go 0 to 2 of 3f of x dx minus 0 to 2 of g of x dx. And that's super helpful because this one I can already replace with negative 3. The first one, I can pull the 3 out in front, and then I'll be able to replace that one with 4. The only way to do this is if we can play around with the rules. Often the rules are something that you say to yourself, well, I just know how to integrate so I don't have to worry about the rules. Then they put together a question like this that asks you to rearrange things and figure it out. Okay, so use the rules, see if you can figure out B, C, D, and E. Are you ready for C? Did you break it up from 0 to 2 and 2 to 5? Get 16. Excellent. And D. You break it up from 0 to 2 and 2 to 4? And then you know 0 to 4, you know 0 to 2, so you can figure out that 2 to 4 then has to be 9. F of x plus 3 is a translation of f of x 3 to the left. Finding the area between -1 and -3 of f of x plus 3 would be the same as finding the area from 0 to 2 of f of x. So here's the idea. If I had 0 to 2, if I know that area, if I move that whole graph 3 to the left, one, 2, 3 to the left. Now I would have -1 here and -3, but that area would be exactly the same as it was between 0 and 2. Does that make sense? So I just translate it back, and since I know that that is 4, the whole area is 2. So there's the first one, remembering that the integral of 3 over x is 3 natural log of x. Here's the second one. I have a little hint. I'm going to have to multiply it out. All right, here's the answer to the second one. Hmm. 22.9. Again, you have to use your calculator anyways, so then the shortcut is a much nicer. If it asks for an exact answer, you can steal the answer from your calculator and change it back to a fraction. Let's see. Like this was this one, right? You have this answer, and then I go math, change that to a fraction. Oh, it's not happy. Okay, never mind. Thought it would change it nicely to a fraction. The fact that it doesn't change it nicely to a fraction tells me that the calculator actually didn't get the answer right. It just got it mostly right. Happy enough.
Why do they get different answers when you do it?
Because I probably wrote something down wrong. Oh, there's a squared. And I never wrote squared. Okay, let's do that again. That's a great question because we screwed up. There we go. 22.9. Let's see if it works now for the fraction. It does. Good observation.
So did we get the wrong answer the first time?
Yeah, we just didn't see that little squared. All right, like I didn't type in the little squared. So we got it wrong the first time for exactly that reason. I will put up the answers for the other ones on the video here. So if you want to check them afterwards, they'll be at the end of the video. There'll be no volume because my mic's out of batteries. Oh, this one, you need your pie plate. Only to figure out that 0 plus 0 is 0. That's the last one.